Welcome to the fourth video of our series. In the last video, we became familiar with creating rotationally symmetrical components. Today, we take it a step further and focus on a somewhat more complex turned part, the crank pin. In this video, we will look in detail at sketch constraints. We show how they help us fully define sketches and explain why that is important. Additionally, we explain how to import an image into a sketch, scale it correctly, and use it directly for tracing. You can download the required image for creation below the video. If you accessed the video via YouTube, simply follow the link in the video description. Before you continue watching, you should download the image. As usual, we start with a new construction. In the workspace, select the viewport element under Insert. Go to Insert from My Computer. Choose the appropriate image of the crank pin from your computer and place it on the XZ plane. You can still move or scale the image, but we will leave it at the default settings for now. If the image is upside down for you, you can flip it by clicking on the icon with the two triangles. We confirm with OK or the Enter key. The image is now added in the browser and the construction history. To scale it appropriately, we right-click on it in the browser and select Calibrate. Now we first click on the center of the front of the bolt, then on the middle of the backside, and adjust the length to 12 mm. You now have two options. Either move the image directly to the origin by double-clicking it in the construction history, or leave the image in its current position and move the sketch later. We choose the second option to learn about additional dependencies. We start our sketch on the XZ plane. This time, we use the Line command to draw individual lines from which we will create the contour of the component. Start at the intersection of the center line and the left outer edge of the pin in the picture. Set the starting point of the line there with a left click. As you move the mouse, a line is created where you can set both the length and the angle. You can switch between input fields with the Tab key. We enter a length of 12 mm and align the line horizontally. You can recognize this by the small symbol for horizontal. With a second click, you set the end point of the line. The next line we draw upwards, ensuring it is perpendicular to the first line. You can set the angle either by entering 90 degrees or by using the blue dependency symbol. Now, draw the rough contour of the crank pin. Dependencies are automatically created in the process. If one is missing, we will add it manually later. Make sure the contour is closed at the end. You'll see it in the rectangular symbol. It's not a problem if the line isn't perfectly vertical. Dependencies are useful because they automatically establish measurements and alignments based on your conditions. That means you don't have to manually measure the length and angle of each line, but can control many things through dependencies. After the contour is drawn, the lines are still blue, which means the sketch is not fully defined. You can test this by grabbing a line with a left click and moving it. To avoid unintentional changes, we should fully define the sketch. First, we convert the bottom line into a center line, for which we simply click the line and select center line. Now we add constraints. We begin with the perpendicular constraint. Select the perpendicular constraint icon and click on the corresponding lines. Ensure that all vertical lines are actually aligned perpendicularly. If an error message appears, it just means that the constraint already exists. As the next step, we set the lines that should be on a common axis to collinear. We align the three lines with a diameter of 4 mm so that they lie exactly on one line. You can check this by dragging one of the lines. The other two lines should move automatically as well. Now proceed to the dimensioning. You can click on Dimension or use the shortcut key D. We start with the diameter of 4 mm by clicking on the line of the shaft shoulder and the centre line. Then we measured the steps with diameters 6 mm and 3.8 mm. Now we add the lengths of the shaft pin steps. We also measure the chamfers in the sketch by assigning a dimension and an angle. It should be noted that we need to add 90 degrees to the given angle. Although this is somewhat more complex than using the chamfer tool after rotation, this approach allows us to fully determine the entire contour of the tenon in a single sketch. This way, we do not need an additional element, making the construction clearer. The sketch is now almost fully defined, but still movable. To fix it at the origin, we use the coincident constraint. Click on the intersection of the centre line and the outer edge, and then click on the origin. The sketch should now be shown in black, which means that the lines can no longer be moved unintentionally. A red lock appears next to the sketch in the browser, indicating that it is fully defined. Now we close the sketch, hide the image, and create the rotation. The feet automatically recognise the profile and the axis, so no further adjustments are necessary. Simply confirm with OK. Since the crank pin is made of steel, we do not need to change the material, save the component. Congratulations! You have successfully designed the crankshaft and learned how to import an image into a sketch, scale it, and use it as a template for tracing. Additionally, you have deepened your understanding of important concepts like sketch dependencies and the full definition of sketches. Moreover, you have seen that the rotating tool is powerful enough to create more complex turned parts with just one sketch and a single rotation. In the next video, we'll focus on the conrod, so stay tuned to learn more practical features.